All right, so thanks for coming to our talk. This is going to be a little bit different than maybe closest to the Bloomberg talk that was yesterday. That's going to be a tough act to follow, but at the same time, I think for every large enterprise installation that you do with Jupyter and especially on top of Kubernetes, you're going to learn a lot as you go. And this talk in the next 25 minutes is our user journey here at from Capital One. So who we are, actually that should have shifted here. So give me just a second to figure out what the slides are doing. Here we go. My name is Dave Hoover. I'm a lead platform engineer over machine learning platforms at Capital One, and Jack's one of my coworkers. We've been together about 3 years, and we build machine learning platforms. We've been doing this for a while, probably too long, kind of like a lot of other folks have talked about working on Jupyter. It's been a long process working on this. And we serve data scientists, machine learning engineers, business analysts, data analysts. About 60% of the data analysis at the company runs through our platforms and all of the machine learning at Capital One. So here's kind of our journey with Jupyter and what we've done. About 9 years ago, we went all in on the cloud, 9 or 10 if you want to think about it. It started in 2015, and our first installation was Jupyterlab on ECS. We had a guy that wrote the provisioner in about 8 weeks, and that survived until this year, because when somebody loads an enterprise critical application on it, it tends to stick around without strong migration planning, and you invariably end up with somebody's pet project at an enterprise like ours. So about 4 years back, we built, after that, so let's see. So right around Jupyter Hub v1, we basically built the second version of it, and that was on Hub. It was let me. Sorry, I'm having some technical difficulties here. It was early Cube Spawner and Zero to Jupyter Hub, kind of like we've seen in a lot of the other ways, or in a lot of the other talks, but especially from the previous talk from the gentleman from the Rubin Observatory, we had problems with a configurable hub proxy. We had problems with simultaneous scaling. It was all on a single cluster, and after a couple years of that, our product management came to us and said, hey, you need to find a way to stabilize this. We had already been playing with Kubeflow pipelines, and if you're not familiar with Kubeflow, it's an open source modular ML ecosystem. We're lucky enough at Capital One to have a couple of the maintainers on staff, but we've still built some stuff on top of it, and we leverage the notebooks and pipelines modules heavily. But what the Kubeflow Notebook Operator has allowed us to do has allowed us to scale from 1 cluster to 5 in east and west simultaneously, and really make this sing at the enterprise level. So we're going to start today at the bottom of the stack and move upwards into customer workload management, and I'm going to hand it off to Jack to go through a lot of the bottom of the stack and the core items that we build on top of, or that we build into the cluster to enable this to work.
Thank you, David. So at the core of our infrastructure, don't fall off the stage either. Yep. At the core of our infrastructure solution is running our platform on top of Kubernetes, begging the question, why Kubernetes? And before I get into that, since some of you might not be familiar with Kubernetes, a good way to think about it is, as a solution for the enterprise, is to think of it as a meta language for cloud resources. Pods, containers, the like, can be thought of as our base primitives. We can build those up into custom resources, operators, or APIs, and suddenly we have submodules of our software program. The control plane we manage is the compiler of this, and it compiles it down into the solution for the enterprise at Capital One. At face value, this might sound like a lot of overhead and complex to manage, and at times, it can be pretty complicated. But the real value is the level of customization you get with building with Kubernetes at scale. This customization empowers us to meet any new needs, requirements, or asks that will drive home values for the enterprise and our users. And if you've ever worked at a large company, you know that requirements change frequently. The most recent iteration of our platform, V3 that David mentioned, currently runs on top of AWS EKS, as shown as the center of this delightful onion graphic here, to represent the base AWS offering with all of the things we put on top of it to make it enterprise approved. The major difference between EKS and the previous cluster management is our managed control plane. We used to have etcd failures and would occasionally lose a cluster due to having to manage it and its database storage ourselves. Rebuilds are not fun for customers or your SRE teams, and the managed control plane from AWS thus far has proven to be 2 to 3 times more scalable and significantly more resilient than when we were doing this ourselves. The CloudWatch control plane logging is a nice bonus for debugging. Now that we have talked about the core of this, once again, delightful graphic, let's take a look at some of those other layers that go hand in hand on the security and access controls, integrating with our enterprise-specific tooling, as well as policy enforcement. As mentioned, running a platform at the enterprise level, especially in a highly regulated environment such as Capital One, requires a wide array of support and governance tools. There is a lot that goes into this setup, and today we'll touch on some of the key tools that keeps our platform running in a fashion that satisfies both the enterprise and our user base. First, let's talk policy, specifically Styra. Styra is the commercial company that was built on top of the CNCF OPA, or Open Policy Agent project. At the core, what they provide is policy as code, providing enforcement across the cluster to provide enterprise security, such as ensuring that no images or pods allow users to run as root within their notebook. In order to accomplish this, Styra uses Rego, which is a policy language, to enforce rules against the JSON and YAML definitions our Kubernetes resources are defined with. Common examples could be enforcing the proper security context on the namespace of our users and the objects they create, or enforcing various label requirements used for administrative actions, such as chargeback cost tracking to determine who did what, when, and who is going to pay for that cost. Here we have a nice AI-generated example Styra policy, which is great because I don't like writing Rego. And in this example, it would enforce that all images running in a user container comes from a company's image registry, here the very cleverly named My Company, and deny any that don't match our policy. This beautiful AI-generated example, once again, favorite thing to hand off to LLMs because I just really don't want to write that. And up next in our governance tooling is Cilium and multi-tenant isolation. So where Styra validates the configuration, is this YAML allowed? Cilium policies enforce behavior, such as, is this network packet allowed? Cilium leverages this by inserting networking logic directly into the kernels of the nodes notebooks are scheduled on. What all this complicated, fancy kernel networking logic provides for us, it can be thought of as namespace level firewalls. Being able to explicitly control the ingress and egress of a user's namespace is one of the most critical aspects of running a platform safely. And in terms of Kubernetes, a namespace is essentially just a user's workspace. It isolates where they work, and all their resources that they create are scoped just to their namespace. Here we have an example of a Cilium policy, which is a default deny policy. By establishing this policy, the endpoint selector selects all pods in David's user namespace and then denies all incoming and outgoing traffic. Starting with a blanket deny all, then allows building up from there, where any traffic or pod-to-pod communication requires explicit permission from the platform administrators to occur. This is critical for a multi-tenant platform by properly locking down each user's namespace to ensure that no unwanted traffic could reach other namespaces on the cluster. Speaking of our multiple tenant, yeah, this is our old version of our slides. Speaking of, so let's talk multi-tenant isolation. So we have a ton of users all on our cluster, right? And they don't know that they're all sharing underlying AWS instant nodes. So by isolating each tenant with some of the controls we've put here already, it ensures that they can share things safely without cross-pollinating or causing issues like noisy neighbor problems and all that fun stuff. This isolation, again, provides safety for our users and for the platform as a whole to make sure that everything runs the way they want it and the way we want it. So now we've taken a look at various enforcement for user actions and resources. Let's look at how to manage the flow of traffic at the application level with Istio.
You're a slide ahead.
Oh, okay. I'm looking at the wrong picture. My bad.
Go back one more time.
Oh, I see. Oh, but that doesn't match the speaker notes then. All right, pretend it's the other slide. Istio's networking enforcement. Ingress and egress rules at the cluster level. A major component is that Istio keeps someone in one namespace from being able to log into someone else's notebook. This verification ensures that only user X can open user X's Jupyter resources, and would be hit with an access denied screen if David tried to send me a link to his notebook. Coupling Istio with OAuth before a user can even attempt to open their own notebook or fail to open someone else's notebook. This is all accomplished via SSO integration. The first level of authentication occurs in the UI via SSO, and after you log in via SSO, your identity token then gives you access to generate a notebook on the cluster. The Istio Auth service and integration within Kubeflow allows our platform to gate Kubeflow notebooks. When I click on a notebook URL, it reads my identity token, matches it to my user identity that goes along with my tenant namespace, and ensures that these match. Basically, gate 1 being the UI, gate 2 being the notebook, and the SSO Istio integration wires it from UI directly to the Kubernetes cluster. All this helps keep the business and our users safe. And now that I've gone over how we lock down our users and prevent them from doing things, I'll hand it back over to David to talk more about how we empower them.
All right, thank you. So we're going to talk a little bit about our user journey and really focus on how this is going to work. How do we give people access to all this cool stuff, but stay well managed? Understanding our users and how they work is the first step here. So power users, our personas break down into two categories, and power users are the first ones. This is, well, the best way to think about it is somebody that has pretty much full control of their namespace and their workspace. This is a technical user. This is someone that will allow to run a custom image, will allow to create other pods, will allow full access to GPUs, will generally allow them to spend as much money as their divisions want to pay for to get their jobs done. And then, so like we mentioned in the lead-in, unfortunately, you're going to get a little bit of switching back and forth because I think my slides and my notes are off by one. So this is what if you're not familiar with it, this is what the Kubeflow Notebook version of Jupyter Hub looks like. And as you deal with this, you can see not only are your resources CPU, RAM, and GPU configurable, you have full control of your workspace volumes. In our case, we bind an EBS volume by default for persistence underneath every notebook, and then we add an EFS storage along the same lines as some of our other presenters have talked about for persistence between notebooks. So there's a life cycle in our systems that allow, or that basically give you between a 1 and 4 hour idleness band that's configurable, and after that it'll shut down your notebook and your resources are saved to your data volumes, so when you bring up a new one, they'll come back up on the same volumes, and you won't lose your work as long as you're not saving to like temporary storage within the notebook itself. All of this power is available to a power user, but what it ends up doing is, in some cases, giving people a lot of rope. The other persona that we have on our clusters and our systems is we have roughly 4,000 analysts that we serve as part of the platform. And our analysts' personas some are very technical, most are not, and they just want a way to get going quickly. I'd love to be able to show you everything that they do step by step, because a lot of that's been custom work over the years. But for all intents and purposes, it's also heavily integrated into our systems at Capital One. And since there's a corporate communications review on this talk, I'm going to try and describe it as very close to how Jupyter Hub in its current form works, but I'm unfortunately not going to be able to show that off. We do similar things to a lot of other folks with our Studio VS Code offerings. We've done some work around combining containers, so our base Jupyterlab installation also has VS Code in it. The Jupyter server proxy project that UV presented on earlier today is a core part of how we expect our users to do things. So they'll spin up a server, whether it's Dash or whether it's even something like Airflow, and we'll proxy that out to them as well within the notebook interfaces. There's a ton of value that we've gotten out of the community here, but at the same time, because these folks are fairly non-technical and because our platform must be governed, given that we're a regulated business, we run into this little thing up here called Hiram's Law. There's two axioms in system design that we run into a lot at the company. One of them is the phrase, the purpose of the system is what it does. And then the other one is basically this: with a sufficient number of users of an API, it doesn't matter what you promise in the contract, all observable behaviors of this are going to be used. It harkens back to the XKCD comic, if you've seen it, the one about someone holding down the spacebar and heating up their system. This is very much our experience with this. When you have thousands of users on a platform, making changes, making upgrades, it's almost impossible to test all available behaviors of your platform. So you're always going to have somebody that's going to come back to you and say, well, what did you do that for? You just broke my workflow. And we find that very commonly across our analytics personas. So how do we then keep things under control? Well, the first thing that's user-facing controls, less so the Istio and the Cilium and the things at the outside are closer to the perimeter, but things that directly affect users' lifespan, the resource quote is the first tool here. And what you end up doing with a resource quota, and what you have the ability to do within Kubernetes, is to set up, whether that's request limits, pod count, storage, and even at the PVC level. This is just kind of an example. I don't want to throw too many Kubernetes manifests at you. However, what we generally shoot for is the equivalent of what the largest available instance node is on AWS. We generally run in the R range, so the memory heavy nodes, and then the ability to run a moderately sized distributed compute cluster underneath of it. So this is sized for a decent sized Spark cluster, or somewhat of a large Spark cluster, depending on what you might consider that, plus a notebook to then act as the driver. As we get further into the presentation, distributed compute is a huge value add to our Jupyter setups. So not only are we serving notebooks, but we're serving distributed compute underneath of it. As Jack mentioned before as well, the other thing that ends up being a primary user control for us, both quotas for resources, but the other thing is preventing root actions and keeping some tabs on what users are able to do in Python. OPA is a core part of the root prevention, but our friends at Anaconda really are the key of the core puzzle piece in order to keep users able to work not as root and to really have a valuable experience on our platform. The difference between Conda and stuff like UV and plain pip or pipenv for us is that we can basically tell users, you can do anything you want in Conda as long as it comes out of Conda. And because Conda will pull in system libraries and will pull in things from other languages, works fine in R on our Studio notebooks as well. Without that as a tool and without that subscription, our platform really wouldn't be able to function in nearly as much of a user-friendly way. We would end up dealing with multiple requests for go and do X installation for me on your image as a user, because I can't do it because I don't have root access. So cost chargeback is another thing. This is there's not really incentives for this from a functional point of view, but if you think about how a business our size works, we have 13 different lines of business. The way it basically translates to the platform is there's 5 different divisions. Each one of those has to be isolated by data storage effectively, and isolated. And the way our security requirements have come in is that has also meant isolation at the cluster level. So 5 clusters underneath the platform, each one build back to a division, but also build back to a certain team and ultimately to an individual. It's a really interesting piece of the puzzle. I guess the other thing to kind of understand with financial reporting and this kind of incentive is it's really a lagging indicator. So it's not something you would tend to see immediately. Nobody's coming for you spent twice your salary in GPU compute last week. What are you doing? It's a lot more likely that it's your team spent your entire data science division's budget for 6 months last month, and we're gonna come shut you down for spending way too much money. That's not entirely unheard of. As platform admins, our customers tell us what they need to get their jobs done. We give it to them. It's up to them to spend their budgets wisely, and occasionally their VPs come for us and say, well, why did you let them do that? And there's a paper trail that has to exist and approvals for that. That's kind of how the megacorp tends to function. We've used KubeCost for this historically. I'm not going to stand up here and endorse a product. It just got bought by IBM. Who knows how well that's going to work in the future. Probably the most important thing with chargeback is making it so that it aligns or integrates with your existing observability solutions and that you can get data to your finance department. That probably is more important than any individual solution here. So the next slide, and we're going to talk a little bit about the Kubernetes API. Just pretend that I'm working a slide ahead here again. So without getting too technical, the Kubernetes API is also your important point of role-based access control. And that's like the last piece of user control here. In our case, the power users have access to the Kubernetes API. They can spin up fully functional Spark jobs. They can spin up fully functional Dask jobs outside of their notebooks. They can work with distributed compute. They can spin up other servers. They can create pods. Because of the other controls that are built around the namespaces, we're comfortable allowing them to do that. And there's no external access or anything that gets out of our clusters to the outside world. But for the non-technical users, they basically get a notebook and some on behalf of patterns for distributed compute, as we'll see here in a second. So distributed compute, overall we offer Spark, Dask, and we're dabbling in Ray and the Kube operator. But if you think about how the industry works for distributed computation, most of it's still Spark, and that's kind of the default. So here's kind of how this functions in our experience on top of a Kubernetes cluster and on top of Jupyter notebooks. There's 3 patterns for how distributed compute works. One is native Spark submit on Kubernetes using a Spark kernel, or just just creating straight sessions on the terminal in Jupyter. If you're not familiar with Dask, it's basically a pandas-esque distributed compute framework. We've invested in our credit divisions heavily in it, but it hasn't ever really caught on the way that we'd liked at the business overall. So that's why we're split. It's something to look at if you're really. It's got nice widgets. It's got really good Jupyter integration. It's something to look at if you're not really familiar with it. But Dask Kube Cluster Classic is a very similar aspect to Kubeflow or to Spark Submit, where you're interacting directly with the Kubernetes API, spinning up distributed compute resources. The second point here is the operator pattern, and this still requires access to the Kubernetes API. So the top two would be things that our power users can do, and then the bottom one is an on behalf of service-based submission of distributed compute jobs, and this is what we give our non-technical users. We've written Dask Gateway is available in the open source. You can pull it up. It's got a traffic proxy in there, and basically that's submission by a user using their notebook auth over to the proxy that then builds their distributed compute job for them, and builds links back to the notebook so they can use the Dask dashboard and the way that that's meant to work. We built a similar service on top of Spark, proxying the Spark UI and building a history server around that back to the user. That unfortunately doesn't exist in the open source, and given our company's history with open source products, it may not. But that's the kind of thing that we've had to construct to keep users away from the Kubernetes API. They're easier to use because they give you the least amount of power. If you look at this, things that are closest to the cluster, and if you've ever dealt with a whole Spark config tuning, it's a beast, but you can do a whole lot with it. And as they get down, they get more defaults, more opinionated, less powerful, but a whole lot easier to use. And that's how our user journey really has progressed across distributed compute. So as we get to the end of this, what have we learned today? The first one that we've learned across 3 versions of our platform has been to beware complexity and over-engineering. We feel it's possible to build a good product in this space, but rarely on the first try. And we've had to iterate through AWS native stuff, we've had to iterate through Hub, we've had to iterate into Kubeflow, and we're still building and trying to make this thing good for our users. And we feel that anytime you end up taking on a big complexity change like we did with Kubeflow, you really should try and balance that with something that helps you out. Because going from Kubeflow and then coming back to EKS took a lot of our SRE overhead away so that we could focus on building things for the users at that point. Strategic iteration is the only way to really do this long-term over a pretty good horizon. And then the second lesson really is we learn this daily: listen to your users. They're going to tell you what they want. Sometimes the answer at an enterprise is no, but usually the answer at the enterprise is, let me go talk to my VP and maybe we can get halfway there now and then we can do more later. And the platform is the enabler of the users. It in and of itself is not the goal here. So as long as we've been able to stay focused on that, we've been able to build what we feel is a pretty good system. And if you'd like to meet up or contact us later about this, I think I'm just about out of time, so I don't know if I'll have any time for questions. But I'd just like to say thanks for listening. I'm surprised to see so many people here at the end of the conference. So, thanks.